Today, I had the privilege of speaking with Scott Walter, who is a robot offline programming pioneer, a co-founder of Deneb Robotics in 1985, and also a co-founder of Visual Components in 1999, where he is the chief technical advisor. He has a BS in mechanical engineering, a master's of engineering in aerospace, and a PhD, all from Cornell University. His PhD thesis was on real-time collision detection of polygonal objects, which came in handy when simulating robotic systems. Today, Scott and I got into factory floor layouts and optimization from the ground up, first principles, A-star searches, orders of magnitude of search spaces, how to optimize things, how to use vision and artificial intelligence to make things work better, and how this all relates to Tesla. So let's take a look. I'll start here. My apologies for looking bad, but I'm like on my laptop because everything else failed. So I wanted to get to talk to you. So obviously I did an introduction before the cold open thing about you, but this is Scott Walter, and we are going to maybe the first of 3 interviews where we're going to talk about a bunch of stuff, but today we're going to talk about some kind of classic machine learning stuff, like you said Dijkstra, which is what A-star is actually based on, if I'm remembering correctly.
Right.
But we're going to talk about some old algorithms that have been around forever, but are still super effective. Order of search problems, how things get around in factories without colliding with each other and into people, and eventually we're going to talk about robots. And what was the third topic we were going to talk about? There was another video we were thinking about, but anyway.
Oh boy, it just came up, but now I forgot. Now the stage fright hits, and I'm trying to remember, but it will come to me.
Anyway, but the cool thing is that you have been designing tools for many decades that robotics tools, essentially, and simulation tools for robots and things. So yeah, we're just going to talk about that, and you should have permission to share the screen whenever you want. So you can
okay, yeah. So maybe a little bit of a history of, well, let's say our conversation. The genesis of this conversation went back to an episode you had, I think, about 2 weeks ago. And of course, here I'm fumbling, showing my Zoom skills of not being able to find share screen. There we go. And we'll finally go ahead and get it and get ourselves up here. And we were talking about whether full self-driving was using like a grid-based method to determine whether there's going to be collisions and stuff like that. And I just kind of reacted in horror, because it's like, oh no, we tried that. That's, I hope they are not going to go doing that. Right. And then we had the discussion, and I think we ended up talking about anything but that.
Right.
And then, it first started out there saying that, well, the reason why we kind of know a little bit about it is that our background is factory simulation and robotic simulation. We really kind of started out in the robotic side of the factory simulation, but to simulate the factory, you've got to simulate all the components of it. And a lot of it is the flow, how these different cells are connected together. And historically, that flow was usually like a conveyor system or something like that. It was moving material from here to there. But that suddenly changed over the past decade or so, that now mobile robots are replacing all the conveyor systems out there. Right. And mobile robots are basically just tiny cars that are driving around by themselves. And in fact, probably a lot of the automated vehicle technology is really coming from the mobile robots more than it is actually coming from the cars themselves, because they're in factories, they're in a far more controlled setting and everything else. Yeah. So we had to go in there and start simulating that process. And you can kind of see it's going along here. They're a little bit autonomous, and they do their best to avoid bumping into each other, but it's not perfect, because it turns out it's easier to tell whether you're going to go into a collision than to actually avoid it. Now, there are situations where one will know to yield to the other, but they kept on getting these situations where they would just deadlock, and then the whole simulation would grind to a halt while the two of them are doing this dance trying to figure out how to get out of the way. So we just said, forget about that. What we'll just do is that if we know they're going to collide, we're going to slow them down, maybe add a little bit of delay, and say in the real world, they'll work it out. Because all the engineer really wants to know is like, I've got this proposal, I'm working on it, I want to see if it's feasible, and there's a couple of questions I have to answer. One is, how many mobile robots do I really need? How much is too much? How much is too few? And what kind of throughput do I want to get? So they really want to get answers, and these are virtual machines. We try to make them behave as close to the real world as we possibly can. But we know there's trade-offs. There's optimizations you have to make. that the more and more accurate you get, the harder and harder it is to get the answer, and the longer and longer it takes to get it. So if you want the answers now, you kind of make some of these shortcuts.
Yeah.
And then
just to give people a little bit, so I've looked at this last time when we were talking, but just to fill people in, the blue and white things are the little mobile robots.
Correct.
The green things are the packages, whatever that happens to be that they're carrying. Obviously input output. One of them is spinning right now, and then the gray area, my understanding is that's the area they're allowed to drive.
Those are basically the roadways. Yes. So they're only allowed to drive on those particular areas, and if they're connected, then you're able to get from here to there. If they're not connected, like in here, there's a gap, so it has to go all the way around the block if it wants to come back in there. And it is aware of obstacles. It's pretty easy to get out of the way of a static obstacle. It's the dynamic obstacles that are a little bit trickier, because you kind of see them coming, you try to figure it out. Oh, I think I better slow down. But at some point, your patience wears thin, like it does in a parking lot sometimes. And like, is that guy ever going to get out of the way? And so that's sometimes what happens, is that it works. And so and what that does is it gives us some keen insights, me personally, on what Tesla is trying to do. And then, how impressed you get when you're trying to solve these automated kind of mobility questions and kind of what they're doing. And we had to use the grid-based way of trying to exclude robots moving into here to figure out, don't go there, someone's there. And it just, like, everything you said about that was like absolutely true. It's like, there's going to be resolution issues. How big should the grid be, or how small should the grid be? How far should it extend out, and everything? We never really got into that too much detail, because the first thing we did is I think we then switched to sort of like this next screen over here, where I showed a much simpler version and said, okay, here's what we're trying to do, is that we have some sort of roadway network or pathways, and we have over here a product is going to magically appear. And for those in the gaming world, you might call it a spawner. In the simulation world, it's either called a source or a feeder. And then it's going to go over to this spot over here, which could be a process point, but in this case, it's just going to be a sink. It's just going to disappear, because all we're trying to do is demonstrate the idea of moving something from here to there. And the first thing out of my mouth was that, what we do is we use A star to solve this. And then you were like, A star. And then the whole conversation just evolved around that. And so that's kind of where we're going to be going.
So actually, before we start this, maybe I had a whole demo before my computer system failed. But let me see if I can share my screen.
Perfect.
And unfortunately, I photoshopped it all out. But okay, so you can see basic chessboard. So can you see my mouse here or not?
I don't see anything. So
okay. So
okay, I'm seeing okay, there we go. I'm seeing something. Yes, exactly.
So basically, we just have the idea that maybe you're starting in this bottom right-hand corner, and your goal is to get to the top left-hand corner. This is not a particularly interesting chessboard, because there's not a lot of obstacles. But basically, what you're doing is trying to find, you can't go diagonally. You can only go straight up or sideways, straight up and down or sideways. So basically, the idea is, how few steps can you get from the bottom right to the top left without colliding with anything? That's the basic goal. So and again, I had it all drawn up where you could see the movement that it would make and all of that kind of stuff. But you can imagine in your own mind, dear viewers, you can imagine how you would calculate this out. And the basic idea is, and the way to sort of mathematicize this is to say, I've come 3 steps, right? So I go 1, 2, 3. So I'm now on this white square above where that brown pawn is down there, to the northeast of that. And so I've come 3 squares. So that means I've done 3 moves. So I've had to pay a cost of 3 moves, right?
Right.
So maybe it's $1 every move, or whatever you want to think about. And then what you need to do is have an estimating function that takes you to the finish move. So what you need is, maybe it's going to cost you another $1 for every move that you make in the future. And then, of course, you can't go into spaces that are occupied by something else. So what you do is you just sort of count it up, and you basically go which one's the cheapest? What's the fewest dollars?
The fewest moves. And a lot of times you're doing that in chess anyways, because you need to get a piece to a particular place. You're trying to figure out, how can I do that in the fewest moves possible? And it's the same thing. So there's the cost of moving around, and if you ask someone, what does A star do? And in the simplest terms is, it says, what's the best way to get from here to there? It just answers that question flat out.
Right.
The thing is that the key word there is best, and best can be very subjective. What do you mean by best?
Right.
And normally people assume when you say best, you mean the quickest or the minimum amount of time.
Right.
And
or distance.
Think about
it could be one of those two.
Or distance, or cost, because you could be considering tolls, or energy. So there is some kind of cost function in there, or even a hybrid of all those things. And these algorithms have been around for a while, let's say in the shadows. People just weren't aware that they were actually controlling their lives in many ways. But they are actually now using them every day, because whenever you do a navigate, Google or anything like that, you say, how do I get from here to there? You are using A star to answer that question. And a lot of times you will see, it'll show, oh, this much time. Oh, this one's shorter, but it takes longer.
Right.
Because it uses side roads rather than the interstate and stuff like that.
Exactly.
And so that's basically based on.
Or you could do the thing,
like
you were saying with tolls. You could say, like, this is the shortest, but it's going to cost you $30 to get there because you have to pay all the tolls.
Yes. So exactly. So you have this idea of a cost. And so you're trying to get, and of course, what a mathematician would say is, what's the most efficient way to go from A to B? And so we have some point A and some point B, and we're trying to figure out how to get there. And we need to create this mathematical model for it. So, what you do is you take a map and you abstract it into some computer database, which is typically called a graph. Now, a graph is very similar to a tree. Won't get into it too much, but it consists of nodes and edges. That's the lingo that's used. Well, okay, what is a node and what is an edge? A node is an intersection, okay? And an edge is a roadway. That's it. So all you're doing is you're saying that with this network, wherever there is an intersection, I put a node there and I draw a line between here and there, and that's my edge. And each edge has a built-in cost function associated with it. We know how long it is, or we know how long it takes to go down there, or we know what the toll is on there, something like that. And it's an abstraction. So in many cases, if you take the U.S. highway network, it will look like a series of straight lines, even though we know that the interstate, is very curvy and everything else.
Right.
So the distance is actually not. I think if you think about abstractly, the nodes don't occupy any space. They're kind of in these arrays, and they may or may not even have coordinate information. They don't necessarily have to. A lot of times, just I need to get to this named one. And the edge functions between them will have it. And usually you calculate it by doing Euclidean distance and everything else. So there's a cost function there. Now, what we need to do is we need to figure out how to get from here to there. And as you can see, there are many ways of being able to solve this problem.
Actually, I'm gonna stop you just one sec, because I know we wanted to talk about the order of difficulty of solving, because the A-star algorithm, the big thing that it does is it uses a heuristic, which is an estimator. And you could also do this in same exact thing. Like, you could imagine that chessboard or this thing by driving every single node and every single edge.
Exactly.
Just going and then you're going to guarantee to find the best solution. But I think you said it scales as the factorial of the number. Is that correct?
Oh no, that's gonna be another problem. That's gonna be another problem we're getting to. That's traveling salesman.
So,
this one doesn't. I mean, this one, I think it scales reasonably. But if you're just to sit there and say, oh, okay, how would I solve this problem? What I've been thinking about, how do you code it up? And you would look at it, you would say, well, in order to find the best route, I have to find all possible routes, right?
Right.
And even with this small network, there's a lot of possible routes. So going from here to there, I can go down here, over here, come there, go over here, come up here, and I could do some silly things and get around there. And there's some shorter routes and there's some longer ones, but you can see that there's many, many different combinations. And as you add more and more nodes, it gets more and more. And that means there's this big exhaustive search you have to go through. And actually, when we spoke last time, I thought that this algorithm was older than both you and I. It turns out, I think it's older than you, because if I'm right, you're right around the moon landing, right?
65, so like a little bit. Yeah.
Oh, okay. So it actually you are a little bit older, because it was published in '68, but the algorithm that it was kind of based on, Dijkstra, predates the space race. It's 1956. So I'm like Sputnik era. So it's been around a while, and Dijkstra is actually called an algorithm. And the A-star is called an algorithm that uses heuristics. And we're going to get into that a little bit, because we were having a little bit of semantic dispute the other day.
About what it is. You know what? Well, this is a totally random thing, but I just realized, I was like, the exhaustive search reminds me of a Feynman diagram. I don't know if you've ever done
mechanics.
But it's the idea of taking every single possible path in the entire universe
Yes.
And so actually I started wondering, oh my gosh, I wonder if quantum mechanics has some sort of built-in heuristics where it's like, that's a ridiculous path. We could go all the way to Pluto and come back again, but probably
yes,
better
exactly,
to go this
exactly. And that's your good point, because in this case, this is a very small network.
Right.
And so if we're trying to solve the problem of you going to your local grocery store,
right.
and if we just have like the local network, it'll probably work out okay. But if we load the entire maps for the US, one of those possible routes is the one where you drive to LA and back.
Right. And we're both on the East Coast. So yeah.
Yes. And you're like, well, that is absolutely ridiculous. Now, one of the things that the algorithm does is it does not allow looping. So you're not allowed to drive around the neighborhood 5 times before you go out. So you're not allowed to revisit it. So that means if you do drive to LA, you have to come back a completely different route. Right. But it's theoretically possible, yeah. And it's just going to be the worst answer possible. So when you think about the entire solution space, it is expansive. It is really big, and as you start increasing these nodes, it comes to a point you think it's just intractable. So there's probably no way to solve this problem, right? So from the first blush, you're like, that's going to be really hard. How do you solve something like that? Well, like you say, there's some heuristics in there, and there's also some observations and cleverness of what you need to do. And I was going to use a downhill skiing analogy, but I think a better analogy is golfing, because probably a lot of people know golfing, and everyone knows what the leaderboard is, right?
Right.
So like when the first set of golfers come in after doing a full 18 holes, someone is the leader at that point. And say someone comes in and he's done a 67. All right. At that point, a lot of people out in the field are very worried, right?
Right.
So you may have a guy that right now he's only done a 63, but he's got 5 holes to go.
Right.
So he's mathematically eliminated, even if he does a hole in one on everything else. So right. At that point, he may as well throw away his clubs and it's all over. Now, if the first guy in, is an 80, then everyone out there is like, oh, I get a shot. I'm going to do it. So what happens is as that leaderboard starts getting smaller and smaller, more and more people get eliminated. And so what happens is that as you are searching these different paths, immediately, as soon as you find one possible solution, bam, you can just start eliminating all kinds of them. And now, of course, you have to be very careful that you don't go down the rabbit hole, which is what I am probably doing right now.
No, this is good. I like this description. Yeah. This is good.
Because if you do like a search of a tree, usually when you search a tree database, and if you don't know what a tree is, you use a tree every day. It's called your file system. You have the root, and your files are in folders and subfolders and all the way down. And if you want to find a particular file, you have to search that whole tree, sometimes exhaustively, to find it. And they do what's called a depth first search. They start at the top node, and they go to the deepest node first, and then they kind of work their way back up and go down again, up and down, and up and down, and up and down, and up and down. And if you're trying to find one of these things, which is basically a random walk, because every time you come to a node, you say, do I go left, do I go right, or do I go straight? What should I do? And the algorithmic approach is you do it methodically. You just go through and try every single combination until you've done all the possible combinations. And that takes a lot of time.
Right.
So one of the things you might want to do is say, well, we don't really want to do a depth first search and down one. What we want to do is we want to progressively go down one level at the same time for all possible intersections, and instead of reduce that, and maybe we have a better chance of getting something. The other is, again, what's a heuristic?
Right. Well, with a file system, a heuristic might be if it's like a business spreadsheet, that if you're organized, you might have your root directory, and then you might have personal stuff, business stuff, and then, like spreadsheets, Word documents, PowerPoint, right? So you could use heuristics to, as a human being, that's what you're doing, right? You're like, oh, it's most likely here. So you can eliminate a whole bunch of trees immediately. So branches, not trees. So,
now, when it comes to algorithms and heuristics, is that they're kind of used interchangeably, especially in a lot of YouTube channels where they're just kind of like, oh, the heuristic or the algorithm. Right. And you can use it interchangeably in your English essay, okay? but in a technical journal, there's a very precise definition. And an algorithm is really very rigorous in what it does and very methodical, and it will just kind of get itself to some sort of solution. A heuristic is sometimes I consider it like a performance enhancing drug for for an algorithm. It's a cheat or a hack,
Right.
or sometimes a rule of thumb that allows you to maybe more quickly get to an answer, because it allows you to do something an algorithm can't. That the problem with this algorithm is that it does not see the map. It doesn't understand the,
Right.
it doesn't see it the way us humans do. We will look at a map and we see it, and our intuition says, "Oh, this is the best way."
Right.
So how do you take some of that human intuition and put that in there? And that's kind of what a heuristic is doing, is that you're taking some observational knowledge and saying, if we do this, it will tweak, it will work better. So the fastest way to get from A to B from your house is, let's just say, I know the grocery store is, let's say it's 5 miles away.
Right.
As a crow flies, is 5 miles away. So unless you live in like the middle of Switzerland where you can see the next village, you just can't get there. Or it's across a river where the next bridge crossing is 10 miles away, you can say, probably I should be able to get there within 20 miles. And if I start going down any routes that are more than 20 miles, that's going to stop. So I'm going to already throw something up on the leaderboard as 20. So that's one thing to do. The other thing you can do is, like, that grocery store is due south of my house. Right. So when I come to the end of my driveway, I'm going to take the turn, which is most south.
Right.
And you do that. And you go down that and you discover, it's a dead end.
Right.
A literal dead end. So, okay, I got to come back. All right. But you don't give up that quickly, because when you get to the end of the neighborhood, you say, all right, I'm going to do that again. However, at the end of the neighborhood, you now kind of check your map or your compass or whatever. And you say, it's actually more south-southwest. So let's find the road that's more south-southwest. So use this, and eventually it will get you there. It may not be the best one,
right,
but it will drive you there, that you now have a pretty good solution on there. And more than likely, the best solution is going to be somewhere around that. And now you just start kind of tweaking and adjusting and making it, and you get in there, and it's just remarkably fast. So it takes what really seems like a hard problem, and as we can see, it can solve it very, very quickly.
Right. So the animation that we've been watching here, is it using the little car is using A-star to discover?
Yes. So basically, it's trying to figure out which way to go. And what we can do to try to, so we can see it's taking a particular route. So somewhere in here, you can say, show the traffic. And you see, this is the way that it wants to go back and forth. And now we could say, okay, what happens if we take this source right here and slide it on so it's starting out somewhere else right now? What's the path it's going to decide to take? And of course, hey, we're not surprised that it's completely adjusted it, because it knows that there's a different way to get there. If we, end up doing something that this pathway becomes disconnected somehow, so I just give a little bit of an adjustment or something like that. So there's really no way to get on there. When it recalculates it, it's going to realize that, hey, I can't even get on there, and then it comes around.
I love how it sat there for just a second when you started it, trying to figure that out. You can see it spinning, and then it was like, okay,
yes. Now there are some little cheats that we do, in that there is a certain cost for calculating a path.
Right.
But once we come up with that path, we keep that solution.
Right.
So we kind of keep it in a cache, and to say, if I'm going from these two again, and we do a really quick lookup, poof, we get that. But then when we see something that's unique, now we've got to go ahead and do that. And then there's the initial little pause where we have to actually create the network. So the A-star network doesn't actually exist at the beginning of the simulation. It's cleared out. We look at all our pathways and we say, where's everything intersecting and overlapping here? Right. We start creating the nodes and everything. So a little of that is the initial setup. But once you have it, it runs pretty quick. And of course, we do not have to always calculate the distance from here to there. That's a one-time cost right up front.
Right.
That you run through. So that's the basics of kind of what A-star is doing. Some of the clever heuristics that they were going to use in there in the algorithm to get it to run really fast. And then it comes down to, well, how do you compare algorithms, one to another? And I guess the other thing is, we didn't really touch on the cost function. So the idea is that as you go down from here to there, each one of these has a distance, and you just add them up. That's your cost function. Right. It's just for every single step, maybe this is 5, this is 2, this is 6, that's 4. You add that together, and that's the cost function for that particular route. And then you do another one, and the score is much higher. And then, that can't possibly it, and that can't be possibly it. And then as I start going over here, suddenly, I take like 2 maneuvers, and already my score is way higher.
Right. So you can just
than
discard
the other one.
anything
So,
going that
you
way.
don't even bother. So you're out of there. So yeah,
And of course, if you're thinking about time, if assuming this thing travels at a consistent speed, time is distance. So
yes.
So yeah.
Yes, exactly. So time might be put in there because you might know what the speed limit is on there, and you know the distance, and from that you can kind of get the time. And then you might have a real-time nature of these things that, you know, you're getting information back to saying, oh, the speed limit might be 55, but traffic is going 30. Right. And then it'll quickly go through and recalculate it. So that seems to be happening when you use these navigation systems. Is it's constantly recalculating it for you just to see, and every now and then it'll just say, hey, guess what? We found a new route that's a lot better.
Exactly.
And now you can imagine if this was a really, really expensive algorithm, they would not be doing that in the background. They say, look, here's your route. Just go ahead and do that.
Right. You can think back to the old days. I mean, you know, you've been around for a while too, but what was that, MapQuest? Where you know, it would run it, but it was on your computer and it would figure out a path, and then you printed it, and that's it. You do not reroute.
I remember AAA triptychs.
Yeah. But I mean, you don't reroute because that's what you got your paper in hand and you're going
you
for
got
it,
that.
So.
Now that is a good thing for anyone who does remember. If you get your old Rand McNally Atlas of the U.S., you know, you open it up and they'll show a picture of the U.S. and they'll show all the major cities, and they'll show a bunch of lines connecting them all. And basically, you're looking at A star, and then off on the side, they will end up having some sort of chart or table that says, okay, you know, how long or what's the distance from New York to Miami. And they already have them pre-calculated. And basically, the way they did it is they said, well, we know what the distance is from like New York to Philadelphia, and Philadelphia to let's see, what are you going to hit? You know, Savannah along the way, and then, you know, from there to Jacksonville and all the way down to Miami. And so they just calculate every one of those things up there, and that is the cost function. And then you can look at that and you say that's the way to go. And of course, they know that's the route you want to take. You're not going to go from New York to Chicago to Denver, to Miami. You know, it's like, no, that's way too costly. So you definitely avoid doing something like that.
These days, the cost function should literally be the cost function. How much gas does it take to drive?
Yeah. And I have noticed that when I've used the navigation, it will come in and show me the eco-friendly route now.
Yeah.
So
it's interesting.
Which is definitely considering, I guess, the price of gas, which could be in there. I assume they're getting real-time information.
Yeah.
So there's no reason why you can't do a lot of these different things. Now, the other thing we kind of talked about here, and we'll see how much of this makes it into the final video, is talking about how
it's all going in.
How do you compare one algorithm to another? How do you know that one of them performs better than another?
Right.
And this is where they start talking about runtime performance, and you will hear people talk about, oh, it's order n or order n squared or order n log n. And the way you typically see it written in a textbook is it'll be like a big O with a parentheses and an N inside. And you just say that. And there's like big O's and little O's, and we won't kind of get into that, but we'll just kind of talk about that. Yeah, it has some sort of runtime order. And where do you get that from? So let's take an example of a very simple kind of problem and an algorithm to come up with a solution. So you have a hat, and I ask you to write down the digits 1 through 10 on pieces of paper and just throw them in the hat.
Right.
And now I ask you to fetch a particular number out of the hat. And the question is, how many operations or fetches is it going to take you to find the one I asked you to get? And now every time you get a slip of paper, you're allowed to take it out so it doesn't go back in there. So it's already taken out. And if you just think about it for a second, you realize, well, sometimes I'll get really lucky and I'll get it the first try. And other times I'm going to have really bad luck and it'll be 10 times. But on average, I can do that fetch in 5 times.
Right.
Well, whatever it is, that's what it's going to be on average. You say, oh, okay. And then you say, well, what if I say put the numbers 1 through 20 in there? And you could quickly come to the conclusion that, oh, yeah, probably on average I can do it in 10 times. Now, now the N in this case is the number of items we have in there. So N is either equal to 10 or it's equal to 20. And the runtime of this thing is N over 2.
Right.
So that's basically how many fetches or operations on average I would have to do. And that gives me an idea of the performance I can expect from this thing. So now typically we don't care about the constant in front of the N, which is like 1/2, and we throw that away.
Right.
And we say that, okay, so that's an order n algorithm, which means it's linear.
Right.
And so
which is actually pretty good overall, generally speaking.
Pretty good. So what that means, if you double the number of things in there, it takes twice as long. So that's a linear performance. So, okay, so, and that makes sense. So if you put 100 items in there, it's going to take about 50 fetches, which is, 10 times more than 10, and that was 5. So yeah, so that's a linear progression. Now, I'm going to ask you to say, all right, I want you to take those numbers in that hat now, and I want you, they're randomly in there, and I want you to order them. So now you've got to take those numbers and you're going to find out some way to order those things.
Yeah.
Now, there are many ways of doing it, and depending upon how efficient you are, if you come up with what might be like the most obvious way of doing it, it's going to turn out that the number of operations you're going to need to sort those 10 items is probably going to be like 100, something like that. Okay.
Right.
And if we go to 20, it's going to take you about 400 operations. And you can say, whoa, wait a minute. The 10 to 100, that's a factor of 10. And you're telling me from 20 to it's something's going wrong here. It's no longer a linear progression.
Right.
And I know someone's banging away in the comments right now. It's like, what about quicksort? It's like, we're talking about the worst sorting algorithm ever, okay?
Right.
The worst sorting algorithm ever is going to have a runtime performance of n squared.
Right.
So that means if you double the number of items you need to sort, you can expect a 4 times degradation in performance.
Right.
And that's when these things just kind of go off to the moon.
Right.
And when you start having lots of items, it takes a long, long time to do it.
And this could actually get us to the traveling salesman problem with, if people don't know.
Oh, yeah.
It's basically, you have a salesman and he or she is starting in one city and they have to visit a certain number of cities and then they come back home again. And the question is, how do you create the minimum amount of time or distance or whatever?
Yeah, how do you do that in the shortest distance and
without repeating any cities?
Right.
So
Exactly. Now, just to kind of put a bow on the other one is that like sorting algorithms are much better than that. And there was like almost like an arms race, I think, in the 60s and 70s between a lot of PhD students and who could come up with the fastest one. And it kept on like going down. It was no longer n squared. It was like n to the 3 halves, and then it was something else, and it was something else, and I think n log n. And now the thing you have to be careful is that it can be an apples to oranges. Just because something has n squared performance versus n or n log n does not mean it's necessarily the worst one for a particular application. It depends upon n. So when n is really big, you go to quicksort. But if you have a really small array of 10 items, you can probably write a sorting algorithm that'll be more than fast enough, and actually faster than quicksort, because quicksort has a lot of overhead and setup it has to do. So it's got to create all these hash tables, all these other things, and that effort makes sense. So when you talk about a line, we really are talking about, remember, it's y equals ax plus b. Right now we're just looking at the x. We said, oh, forget about the a. Remember, I said get rid of the 1/2. And then there's this constant c. And that's kind of the offset that tells you, well, how much effort goes into it. And what that means is the crossing point of where the line and where the parabola cross is not necessarily at the origin. It could be way up somewhere else, and it could be a lot of items. So you have to start looking at that. Now, the traveling salesman problem, that's an interesting one. It has a long history. I'm not sure, but I think someone like Hamilton may have first come up with it. And I think the idea was like, what was the most efficient route to visit all the medieval fairs in Switzerland or something like that. So all these cities had these fairs, and you could pick any starting location, and which was the one that would result in you wearing out your shoe leather the least by walking all of them. So you want to minimize the distance to traveling and seeing all of them. So we can imagine a situation like that here in the US. We can say, okay, I want to go from Boston to Albany to Buffalo to Detroit to Chicago to Seattle to Portland, down to San Diego, Albuquerque, San Antonio, Baton Rouge, Athens, Washington, and that. And what's the most efficient route to do that? And you'll say, oh yeah, basically you just named it off. I mean, that is probably the most efficient route. And there's not much more to think about it. But the reality is, if we start throwing in the middle of the country, we start throwing in Wichita or Boise and Denver and a bunch of others, and we now have a very random thing where things aren't kind of along a perimeter, it's not so obvious what that answer is. And it turns out it's very much related to A star. You have to consider all the possibilities.
Right.
And now all the possibilities become rather interesting in that they actually become a factorial.
Right.
So if you have, just two dots, the possible combinations is like from here to there. That's it. If I get three, I
That
can
was
go from
easy.
here, there to there. Okay.
Yeah.
And then you get the fourth, and now you get a diagonal between them. And it doesn't look like very much. Then you get a pentagram, and you start doing that, and you start seeing it. And as you start adding more in dots, there's more and more lines, and then we get more and more. And then there's just a lot of these different combinations.
Right.
And so the runtime order of the traveling salesman problem is n factorial.
Right. And just so, if for people who may not know the math, if you're remembering back to high school, factorial is just like, if it factorial of 5 is 5 times 4 times 3 times 2 times 1. So you just do it times each of the integers below it until you get to 1.
Yes.
And so just to show how crazy this gets, how fast, I actually calculated this earlier today, but if you have 5 factorials, so if you have 5 cities, there's 120 possible ways of doing it. That's 5 factorial. If you have 10 cities, so you just have 10, double the amount of cities, it was like 16.2 million possible combinations.
Yes.
So all you've done is gone from 5 cities to 10 cities, and suddenly you've gone from 120 to 16 million possibilities. So it goes, it explodes.
It grows. And there are some situations where the solution is very trivial, and others where it's very, very hard. I should say, you can see that, the answer is obvious. So like a bunch of cities along a straight line. Well, you start at one end and go the other, and that's the answer.
Yeah.
But when they start to really become random, it's something else. And it does have very important applications. I mean, just think about your UPS driver every day. He basically is a traveling salesman. He is trying to find the most efficient route to be able to drop all these packages. And every day, the stops he has to make are completely different. Right. So it's not like you can solve this once. And it does become very explosive. In manufacturing, we do that. I had an example where I had to offline program a part. And the CAD data came in where all the holes were, and I was able to interrogate the CAD, say, here's all the holes are, to come up with my robot program. And I run the robot, and the robot is like just bouncing around randomly all over the place. Like, oh, we don't want that. There must be a way to make it a little bit better.
Right.
So I said, oh, okay, let's try to organize that. And I said, well, you could probably do it manually if you wanted, but hey, I'm a programmer. Let's come up with an algorithm. And then, I read up about the traveling salesman, and the algorithm is probably one of the easiest algorithms to write on all time. It literally is a couple lines of Python code.
Right.
Whereas the A-star algorithm is a lot more. I mean, there's a lot more going on in there. So as far as simplicity, it's incredibly simplistic. However, it takes forever to come up with a solution once n gets big. And I mean, n in this case is like 10. And usually you don't consider that to be very big.
Right.
And now,
well, I was just thinking, like the UPS driver, for example, if he had 100 stops in a day, I think, what did you tell me? It's something like 10 to the 100.
10 to the 157. Okay.
Yeah.
So that's 1 with 157 zeros after. Okay.
Right.
You add one more stop to that. One more stop. It's now 101 stops. You've got to multiply that by 101. That means it's now 159 zeros.
Right.
Okay. So this is how the factorials just take off. Just give it an idea of how big that number is. That is larger than the number of galaxies in the universe.
Right.
It's also larger than the number of stars in the entire known universe. Not only that, it's more than the number of hydrogen atoms in the whole universe. And we can break it down even further. It's more than all the subatomic particles in the universe of ordinary matter. Now, if you want to throw dark matter and dark energy and all those in there, they don't even come close. And we're talking, they're off by orders and orders and orders and orders and orders of magnitude.
Right.
On just how ridiculous this problem is. And I first noticed that as I was doing my little problem, and I had everything set up. And this is why you should always save and you should always test on something small. I thought, I'll just go ahead and try it for for 5, it worked. And I tried it for 7. And then, took a little while. So, I wonder if I try it for 10 of these holes.
Right.
And I'm sitting there. And suddenly my CPU fan kicks in. It's spinning and spinning and spinning. And that's when I went back and said, oh my God, this is not going to return.
Right.
It's just crunching and crunching and crunching away. And so that's when you have to start using heuristics to solve the traveling salesman problem.
Right.
And some of the heuristics are interesting. You know, the probably one of the most common ones is something they call the nearest neighbor.
Right. Yeah.
And this will show you why a heuristic can easily fail.
Actually, can we stop sharing just because we can get bigger us?
Yeah.
People are going to be bored of looking at this little truck driving back and forth.
I agree. So I will absolutely stop the share right now. And of course, the thing is, once again, I'm going on down here. It's like,
I'm afraid people are going to be like, oh my gosh, it should be at the top of your screen.
Oh, there it is. Okay. Oh, yeah, that's right. You see what ends up happening is I use Teams every day. And so I'm so used to that interface. And then you get something else. And then I look like a noob. Okay. So
it's all good. I was just like, people are going to go crazy, like watching this little thing run back and forth.
Yeah. It's like,
but I mean, just to put that, I mean, that thing is kind of, if you added a bunch of stops, that thing would be a traveling salesman problem. The little robot, if it had to go to 5 places and then it had to go to 10 and then it had to go to 100, you know, it'd become very quickly intractable.
Yeah. And this is what becomes one of the, you know, in manufacturing, it's very important because sometimes, you know, again, it's like a robot is going to be doing a drilling or riveting or something like that.
Right.
And they're not doing just, you know, 5 or 10, you know, they could be doing 100 of these things.
Right.
And sometimes it might be obvious. Like if you have a chessboard, the solution for the traveling salesman problem with chessboard is trivial. You just go up, back and forth and back and forth. That's it.
Right.
So there are some situations where it's very easy, or you might have some runs of it where it's pretty easy, and then you get some randomness and you're going to try to figure that thing out. But it can take such a long time. And I think what I kind of mentioned is that the thing about an algorithm is designed to kind of give you the optimal solution.
Right.
The heuristic is designed to give you a solution in optimal time. Right. So you don't have to wait forever. And
that's a huge distinction.
Yes.
Because again, maybe the UPS driver would save a couple of dollars in gas if they have the absolute perfect. But if it takes the age of the universe to calculate out the next day's route,
it hasn't saved anything. Yeah,
it's just like, the guy's going to be sitting there and he'll die of old age, and his son or daughter is going to, you know, they'll be waiting.
Yeah, exactly. You're still going to be waiting on that answer, and so we don't know. And again, just to give you an idea of like that. This is a problem we can't solve very easily, is that the US is made up of 50 states. And last I looked, each state has at least 2 cities. Okay. Right. So if you just pick 2 cities from each state and said, let's do the traveling salesman problem for the US, you wouldn't really be able to solve it. Now, there are heuristics and people who claim that, oh, you know, they can kind of do it. Like, I believe there is a traveling salesman problem that works for Sweden, that they've gone in there. And they might be there, or it's one of these things like we're 99.9% confident that this is the solution. Right. And remember, the solution depends upon your starting point. So if you decide to pick somewhere else, it's like, well, you might have to do the whole thing all over again. Right. So it just sort of shows you that what seems to be a simple problem can be really hard, and what can be a really hard problem, you could be surprised at how elegant and how easily computer science come up with a solution to that. Right. And, you know, again, like a heuristic, the nearest neighbor example is like, okay, I've got a starting point. What I'm going to do is I'm going to look for the nearest neighbor to that point. And that's where I'm going to go. And then from that one, the nearest neighbor, and you keep on doing it. And that might kind of work, but you may get the situation that I've got a point here and I've got two nodes right there, and I decide to go to this one. All right, the next nearest neighbor for this one is not that one that was right there, but over here. Right. And then you just keep on marching away and marching away. You get further and further away from that one that was so close to the very first one at the beginning. And at the very end, you suddenly realize, oh, I haven't gone there yet. And suddenly you got to come all the way back. And there could be a bunch of these little kind of cul-de-sacs you forgot to go around. And suddenly you're seeing, oh, I was doing really, really well. And then suddenly your program goes zoom, 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 back and forth. And it just, it doesn't look good. So, you know, there's different approaches. I found that what you had to do is you had to do a hybrid. I did a nearest neighbor. In other words, I would pick the 7 closest nearest neighbors because I knew factorial problem worked for them. And I would solve it there. And then like whoever was the last one out, oh, okay, let's do his next 7, excluding the ones that we just kind of solved. And those are the kind of approaches you can do. And it gets you that answer in the optimal amount of time. Right. Right. Yeah, it's pretty crazy. Okay, so let's tie this all into, I mean, I'm sure a lot of people are like, oh, Tesla, gigafactories, or plenty of other companies as well.
But Tesla, the diagrams that you've done, they use kind of that, at least from what I've been able to determine. They have little roadways and autonomous robots. So how does this, how does this actually affect a real company like a GIGA Texas, for example? They're putting in these roadways. They've got these autonomous robots.
Yeah.
How do they figure this stuff out? And when things inevitably change, which is the whole point of having these modular robots, as opposed to the old school like assembly line where it just like went down the line and you could never make a change.
Yep.
So yeah.
Well, I wish I knew the answer for that definitively, but I'm pretty sure they're using some pretty good planning software.
Right.
There's no way you are able to create a factory like that without some sort of planning software. So they've gone through and they've worked out a lot of the details on the logistics and everything else, and they've gone in and they've probably brought it up to a state, and then some of it they're probably just doing actually in situ. They're trying to tweak it and improve it as much as possible, because sometimes you can sit and spend so much time planning, you never actually get anything done. That a lot of times you just decide, just do it. Exactly. And so the way Tesla works is I'm pretty sure they did a certain amount and said, it kind of checks out. Let's go ahead and start doing it. And then we'll start refining as we go along. Right. And when you listen to people like Joe Justice, that sounds exactly what they're doing, with the whole agile manufacturing, is they probably get something up and running that ended up being kind of like that first route found an A-star.
Right.
But then they realize, we've got a bottleneck here. What can we do to improve that? Can we do to improve that? What can we do to improve that? And so they keep on throwing whatever force they have to on there. And I'm sure they're using some pretty advanced visualization tools. I don't know that they've built any in-house. I think they are using some of the third parties. My suspicion is they're probably using a competitive product of ours, but it would make sense because that's probably Siemens, because I think that's the software that they are using. NX is what everything's on there. So that makes sense. The company I'm from, we're not a CAD company. We other people create the CAD data. We just kind of bring it in to try the representation and add the motion and everything else to that. So that's what I suspect they are doing. And, so as an outside observer, that's about the best I can do, except to say that they had to be doing that because that's what all the other automotive companies are doing.
Yeah. And I mean, it's a much more complicated, I'm sure people are kind of like, well, that's not a very hard problem, but it actually is a really hard problem, because not only do you have, it's big. So it's like, this thing is like a mile, like not quite a mile long, but it's like, it's like 3/4 of a mile long and really big, but so it's huge. And the floor space is relatively open. Of course, they have pathways that can go on. Right. But then there's human beings and other robots and stuff that just is getting in the way. The environment is changing. Yes. And because it's Tesla, they could say like, instead of bringing the raw material metal into this bay, we're going to change it to this bay. So all of a sudden, it's got to change its starting point.
You've got to think about the material flow, and it gets kind of crowded, moving everything around. Everyone's getting in everyone's way, but you kind of work that out to make sure the material can flow. And usually, what happens is that you have these fixed operations that are happening along the way.
Right.
And usually they have some sort of takt time they're talking about, which is going to be under a minute. It's probably going to be something like 45 or 49 seconds, that you have some particular operations that you have to be done with that, and it moves on to the next one, and then you start over again. Now, if for some reason you are having problems, you are what they say in chemical terms, the limiting reagent to the reaction. And everything downstream of you is going to be starved, it's going to be really slow, and everything upstream is going to back up.
Right.
So that's why they're constantly going and looking to where that bottleneck is, to try to ease that bottleneck and make sure everything's going through. So in the planning phase, they have to look at all the operations. So one of the typical things, you've got spot welds on a car.
Right.
And you've got that takt time, and you look, well, how many spot welds are going to be? And there's usually a couple of thousand. And you usually know, well, depending on what the robot is, maybe I can do a spot every 2 seconds, something like that. And so you break it down, you might say, I have 20 spots in the cell. Right. And I figure out which ones are going to be there, and they're critical ones. You just can't do any old spots. It's like, I like to say, like, when you put change your spare tire, there's a certain order you have to put your lug nuts on, and that's the case that you don't want to use a traveling salesman problem, right?
Right.
This is a problem a roboticist will have. A roboticist is trying to minimize cycle time.
Right.
And sometimes he's optimizing the wrong thing. You're trying to optimize the process. So in the case of putting a spare tire on, the optimized process is the star pattern on there and not going around the perimeter.
Right.
So the same thing's going to happen with their car bodies. Just don't do any old welds. There's some critical welds you get at the beginning there called the geo welds that give you the structural integrity.
Right.
And once you hit those, then you can do that. So, they're going through and figure out what belongs here, what's going to be there. And we're going to have not just one robot in the cell. We're going to have 6 of them. They're all going to be getting each other's way. And we've got to go in there and we've got to do it in 49 seconds. And then a lot of times they will break that down. And they'll break it down in the meeting. Everyone will do that, and every now and then there'll be some jockeying. I want that weld. No, you can have it. But at some point it's there, and everyone's like, yeah, no problem, right? Then they get out on the floor, and suddenly some guy's sweating bullets because he can't get it in there because the reach of the robot's not right. They didn't design the end of arm tooling correctly. A fixture's kind of in the way. And it's like, I'm at 49 and a half seconds. Right. Unacceptable. You've got to be under 40. And not only that, you want a little bit of a spare because every couple of cycles, you've got to do a tip dress in there.
Right.
So
I mean, one thing that it brings to mind immediately is the advantage of something like a GIGA press, because the number of spot welds you remove really reduces the amount of time.
When that came out, the first thing I said, people don't realize this is actually going to hurt a lot of my customers, because a lot of people that use our software are using it for those kind of things of doing underbody welding and putting it together and all the fixturing and trying to show what the robots are going to be like. And I'm like, wow, that's easily, several hundred robots. And our parent company is, I have to get it out. Is KUKA.
That's what they make.
KUKA is the robot company that is used primarily and that's a story in itself. That marriage comes from the island of misfit toys, which we can get into in some other state. But
we're definitely going to do another video where we specifically talk about robots, and actually the picture behind you, because we're going to talk about Starship with robots. So I guess there it is. It's down there. It's a little tiny, but
this is one. The reason it's here is I did not lift this from the internet. I actually took it myself.
There you go.
So I was
pretty cool. So we're going to do it future. So stay tuned, because we're going to do one on heat tiles on Starship. So that's cool. But the other thing, besides the GIGA press, it makes me also realize, I think about the cycle times and bottlenecks, but also the variability, because if the process is variable, it could take between 45 and 50 seconds. You probably have to build a 50-second time window for that. But that means that you could be potentially wasting 5 seconds every single time you cycle this.
It depends upon whether it's a manual cell or whether it's automated. If the robot's in there, you're almost guaranteed that that's the cycle time you're going to get. And if the variation is in there, it's very, very small. It should be able to.
I guess what I should say instead is the optimization. Like, let's say you don't optimize it perfectly and it's 50 seconds and not 45. The cost of 5 seconds over thousands of cars is huge.
Could be a lot. It could be a lot. It could be, it's like, well, wait a minute, that's one cell we didn't need. We could have taken that cell out. Or we can end up doing the production. But that is always a problem. There's variability in there, because you have to realize there's going to be failure. There's going to be some preventive maintenance. There's all these other things. Sometimes you run out of material. So you're always trying to figure out how to do the changeover material without impacting what's going on. Sometimes that's the variability of the cycle time, because you may have a robot that's picking up a part from someplace, but the bin it's picking up from, it keeps on getting deeper and deeper. So that means the robot takes a little bit longer to go down and get it and bring it up there, or it's over here. So there will be those little things that will add the variability that you kind of have to know about when designing the process. So you're right. They have to know what's going to be the maximum, what's going to be the minimum. But the real problem is that when you have manual labor involved in there, then it can be a lot. And if a person is suddenly having an issue, or the person has to take a break for some reason, you've got to make sure someone else is in there, or else the line just comes to a grinding halt. So it's it is definitely a challenge to try to figure that out. And when companies are doing these simulations, they are looking at the utilization of the resources. And they're saying, we expect the human operator to have a utilization rate of 85%. So that means that person, and it's like, wow, that's an 8-hour shift. Or actually more. Sometimes it's more like close to a 10-hour shift, and there'll be breaks and everything else in there. But that's a long day where it's like, wow, you only have like 15 seconds to catch your breath before you're going through that again and again and again. So, my hat's off to those people who do those jobs, because I know I couldn't do that. I am not made of that kind of metal that I could do something like that. So I have tremendous respect for anyone that can go into that kind of environment and then do that on a repetitive basis every single day. And they are very clever because the engineers will design the cell one particular way, and they will figure out a way to optimize it better than what they had. They know a trick or two.
Right. Yeah. And, and if they can save themselves a little bit of time and effort, then that's good too. So,
yeah. It's very good. Yeah.
Cool. So, I mean, I don't know if you have other stuff, but I wanted to, at least before we finished up, touch on, you'd mentioned like how AI, how digital self-management, things like that might impact this as well. Like the vision system in particular. Because Elon Musk has talked specifically about that before, that he said that full self-driving is actually an outcome of the factory vision system. It wasn't like they set about to do full self-driving, autonomous driving.
Yes. I'd say the one thing, and this is just being, an outside observer and confirmed by a lot of other sources, I guess you can say, is that the one thing that both SpaceX and Tesla are very good at is measuring things.
Yes.
So there's two ways you can get precision. One is you can like over-engineer something and have really expensive hardware, or you can just be really good at measuring things and knowing where you are. And if you're able to sort of conquer this whole machine vision thing and being able to see where things are, that helps. And then this next episode we're thinking of doing, we'll be talking my speculation of where robots could be used in the manufacturing process at SpaceX. And a lot of people say they're using robots, but no one's quite sure where they're there. That's very key to what they're doing, is that they must have some really good vision systems in there to sort of track exactly where the robot is, to make sure that whatever it's doing is doing in the right location. Because you have a rather crazy workpiece there that's very different than the traditional ones.
Right.
So in a lot of manufacturing, the robot can act blind because the fixtures and everything are holding everything exactly where they're supposed to. So it can basically close its eyes and it knows the part's just going to be there. It's just going to do it. But in other cases, you bring in a part with such variability, you have no idea it's thrown down there, and the robot really needs to get an image to figure out where it is and then adjust and go in and get it.
Right.
And I know what the third. I remember what the third one is now.
Oh, you do? What was it?
We were gonna have rampant speculation on what the Tesla bot's gonna look like.
Yes, that's the third one. Okay, so stay tuned for both of those. That'll be really fun.
Yeah.
I know you have a lot of very specific thoughts about that. But to go, just to tie this in, because we've talked to Joe Justice before too, but he specifically talks about the paint shop and how the vision system is critical to that, because what it can do is almost instantaneously, it can look over the paint of a piece and it can determine whether there are flaws in that paint. And he was saying that, generally speaking, number one, you can test every single object in that case, every hood that comes through, you can check it. Whereas you would have to spot check it if a human was doing it, because it would take them hours. To me, your description there, to me, just sounds like classic Tesla. Right.
Because classic Tesla is they first do the process the way everyone says it's supposed to be, and they get absolutely horrible results, and they get beat up about it. And then they come back and they leapfrog over everyone else.
Right.
And the way the painting process is done right now it's very, very hard. We actually do some paint simulation to try to help people, but that is only a guesstimate, because there is so much going on in the cell.
Right.
As far as downdrafts and the shape of the part and any sort of turbulence that's going to be going on there, and it also depends upon the type of material.
Could have an effect.
That's going to be absolutely controlled. You've got to have the environment absolutely controlled, and then of course the pigment and everything else you're using completely changes it. So I was at a paint vendor where they were doing that, and you just will not believe all the test runs they do of the program. Again and again, and then they have to go and they have to measure, and they see, oh, that's not quite right, and they got to make this adjustment. And it is so tedious. And he's like, oh, you're done, right? It's like, oh no, now we move on to black. Right. What? And it's like, so you got to go through the whole palette, and you got to get something completely new.
Right.
And so I could imagine they probably looked at that and said, this whole way of coming up with, the paint optimization is insanely crazy. There's got to be a better way. Right. What are we good at? Oh, well, we're really good at computer vision and measurement. And I could just imagine, like, oh yeah, they get something there. They right. Definitely have something.
But anyway, so overall, it's just like you said, if you can measure it super precisely and especially automatically and rapidly,
yeah,
that just allows you to be incredibly more efficient. I'm just thinking about even the positioning of pieces and things, right? If you're going to do a spot weld, if you can measure with great precision where those pieces are before you spot weld, the odds of it being a good weld are much better. Slippage or something.
Yes, exactly. And so you're having all the fixtures that are trying to hold it in place. There could be a variety of reasons why it's off. And the other thing is that the reason why, well, first of all, robots are not accurate. I want to dispel this myth that robots are accurate. They're not accurate. However, they're very precise, which means they're very good at repeating their mistakes.
Right.
So whatever inaccuracies they have, they can do that consistently. So if you are telling the robot to go to some Cartesian location space, you will be disappointed that it won't be there. And there's a variety of reasons. Right. It's not just the robot itself, it's the end of arm tooling. If you don't exactly know how long your screwdriver is, or you can't tell the robot, it doesn't really know exactly where the point is that it's supposed to be turning around or anything like that. So you need to get all that stuff down. But even when you get that under control, it's a little bit off exactly where the workpiece is going to be. Yet we humans seem to be pretty good at that. And so again, this is first principle thinking. If you look at the rigidity of a robot and how strong it is, how good it is able to repeat something, and you compare it to a human, we're terrible. The mechanics of our arm, we're really sloppy. We don't have a whole lot of strength. We're really inaccurate. But how is it that we're able to be very precise on things?
Right.
And that's because of our vision system.
Right.
Our vision system is able to compensate.
We're not very precise, but we're really accurate. I think that's what you
Or maybe we're very accurate. And the other thing is, as soon as I grab a pen, I'm able to immediately center my focus from the middle of my wrist, which is what I was thinking is that's like what we would call my tool center point, to that. And I just know it's there now. And I'm completely able to adjust my kinematics to be able to deal with the fact that I have this new offset. It's really magical how we're able to do that and compensate for it. And again, so that's the key to robotics going forward, is coming up with the system which is able to accurately measure the environment, figure out what's going on in the environment, and do it.
Yeah, because if you have like robot eyes that can say the point of your Phillips head screwdriver is, exactly 3 millimeters away from where the thing is that you're trying to screw in the screw, then you can adjust that, right? So it's the problem with robots.
Exactly.
It's basically like if you said, okay, build a car, but put on a blindfold first.
Yes.
You're like, oh crap.
Yeah. And they will do that, because the thing about, an end of arm tooling is, even though it's very rigid, it can get dinged up and hit things. And so they will bend. And there are a lot of robotic systems, especially when they have a tool changer. So you can imagine, if you've got a robot that's going to keep changing its tool, over time, it's going to drift.
Yeah.
And so when they pick it up, they go over and they actually have a funny little ring with a laser in there, and they kind of go in and then move that thing around to figure out where that is. So they are doing exactly that. There are systems that are trying to calibrate it on the fly, because if that thing's off, the whole process is just not going to be correct.
Right. So cool. So I think, so we're tailing into robotics. So let's put that off for the next talk.
Yep.
But I think this is great. I mean, I think it's fantastic to think about just going from first principles. How do you maneuver around and go from place A to place B? I mean, everyone's like, oh, that's simple. But, when you think about it, it's not that easy. If you had to, we got pretty good at it in the old days, but if somebody handed a young kid these days an atlas and said, get from New York to Colorado to Denver, they probably would have some issues with that, because how the hell do I solve this problem?
Right.
But anyway, that, and then transferring it into a factory like Tesla, and how the optimization for time is so utterly critical. It's like every second you're wasting is cars that are not being made.
Yes.
So just optimizing every piece of the entire flow. And yeah, it's kind of overwhelming. I mean, you do this for a living, but me just looking at it from the outside is like, oh, that's a hard problem.
Yeah, it is. And every time you run into it, the questions that people are asking are always different than the last time.
Right,
So
right.
you're always having to say, oh yeah, how do we answer that particular question? That's a unique proposition that someone's coming up with.
Right. So, all right. Well, anyway, thank you so much. And like I said, I really am looking forward to the next one and the next one now that we remember what it was.
Yeah.
So again, thank you to Scott. I don't know if you want to say any last words to everybody, or else we could just, wave goodbye. And
oh, gee, I should have had a prepared statement, but no, thanks, John. This has been a lot of fun, and
cool.
It has been informative and instructive for me as well. And hopefully everyone else has learned a few things along the way, and the comment section isn't going to be too brutal.
Well, we got geeky, but we warned everybody at the beginning it was going to be geeky, so that's fine. So
okay.
All right, everybody, have a lovely day. We'll talk to you later. Bye-bye.
Okay, cheers. Bye now.